Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We only have two last structures to do. So we're going to talk about aromatics, and then a branch that's like aromatics. Aromatic hydrocarbons are based off of a benzene ring, C6H6. Now, the structure here was first identified by a scientist named Michael Faraday, but the actual understanding of it came by a later German scientist named Friedrich August Kegel. Now, I hope I said that right. Now, what we have here is we have double bonds, and it's going to be in a resonance structure. So in order to do that, chemists just make a circle in the middle. That means that there's resonance between the two different structures. And when Kegel came up with the discovery of the structure, he was working on it and took a nap. And in the dream, he dreamt that there were 6 snakes, and each bit the tail of the next, and 3 of them swelled up. And so that's where he got the idea of a structure of a double bond resonating back and forth, C6H6, and that is what, and if you ever smell them, you know that aromatic, it's like the glue smell, that's what those are. All right, now there are 1, 2, 3, 4, 5, 6, 7 structures that we have to name specifically. The first one over here is ethylbenzene. That makes sense, just sticking any additional group on there. Next, we have phenol. Phenol is a hydroxide. It's a hydroxide, we call it phenol. If we have just a CH3, that's toluene. It's not methylbenzene, it's called toluene. All right? If we put an aldehyde, a carboxyl and an H, we call that benzaldehyde. If we put a NO2, we call that nitrobenzene, and that's important because we'll talk about that later. If we put a carboxylic, we call it benzenoic acid. And then finally, if we put an amine, we call that benzanamine. So those are the 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7 structures you need to know. And you simply have to memorize them, to name them. All you have to do is know if you see a benzene ring, it's aromatic. That's all we're doing at this point. All right. Now, if we have 2 additional groups on it, there's a specific way we do it. If they're at 1 and 2, we call that ortho. So this would be called orthonitrobenzene. If they're at 1 and 3, we call that meta. So this is meta-nitrobenzene. And if there are 1 and 1, 2, 3, 1 and 4, we call that para-nitrobenzene. So those are the 3 different ways we can met it. And if on the other side, then they're just counted from the other direction. And so they're always just ortho, meta, or para. All right, great. Next, I want to show you the structure. I think this is really cool. People don't know so that. You know that this is toluene, and there are 3. But before we do that, those nitro groups have a lot of energy in them. So we could try nitrotoluene, take that apart, TNT. This is the makeup that makes up glycerol, which is extremely explosive because actually nitroglycerin. Nitros have a lot of power in them, and this really wants to get rid of that. That's why there's a shock value. And it was Albert Nobel, who first came up with a way of stabilizing that to make dynamite. All right. Now, the other structure we're looking at here called polyaromatic hydrocarbons. So we have more than one benzene structure ring incorporated there. Now, the problem with polyaromatic hydrocarbons, if you've ever seen a freshly paved road and you see that sheen when it gets wet, those are polyaromatic hydrocarbons, and they are soluble. Now, when you take a regular benzene, it's poisonous to the body, but the body can process it out. It does that by making a hydroxide, making a phenol, and then it can process out of the body. With a polyaromatic, what happens is each forms a phenol, and then it, through dehydration reactions, we form what's called an epoxy. The body can't process that out, and so it gets stuck in the body, and that's why we can really get some bad things, cancer and things along those lines, from polyaromatic hydrocarbons. All right, last process, and we finish up here, is called saponification. It's the making of soap. Okay, it's a reaction of ester with a basic structure. So if we take our ester, our oxygen, our carboxyl with a chain on both sides, and take a base, lye was used a lot of times, we're going to generate alcohol. And then the other side is the soap molecule. So we're going to have that negative, and this will all go in the dirt. This will go into the water, and that's why it works, because it pulls it right out of there. We've now developed. Let me explain a little better. This R end is a nonpolar end. It goes into the dirt because dirt is nonpolar. This negative end here, that is polar. It will go into water, and so it works in that way. Safer, softer, less alkaline soap systems. Back in the day when they first came up with soap, it was so pH basic that it would actually burn the skin, and so people take a bath once a month if they had to, because it was really. But as a result, now soap molecule both polar and nonpolar. So the nonpolar end dissolves in the dirt, and the polar end is also this end here dissolves in water. This end here, the nonpolar dissolves in dirt, and that pulls it through, and that's where we go. All right. Now we're going to practice some. Okay, so here is the practice, and all I want you to do is identify if it's an alkane, 1 alkene, 2 alkyne, alcohol, carboxylic acid, ester, ether, amine, amide, aromatic, polyaromatic, aldehyde, or ketone. And there are a total there of 30, I believe. Yeah, there are 30 structures. So copy those down and then work through them. Okay. Any questions, let me know. ltswpd@gmail.com. Remember to, through ltswp@gmail.com. Remember, like, subscribe, share. Any questions, let me know. Comment, I'll be glad to respond back. All right. And here are the answers. Good. All right. Thanks a lot. Take care. God bless. We'll have 2 practices tomorrow and we'll be done.